So welcome to the second great day of Smalltalks 2019. And we don't want to start with boring stuff. That's why we're going to start with Boris. No, just kidding. And just because of the name, boring, Boris, you know, that's a good joke, isn't it? So anyway, this is the VM track. Yeah. So what Boris is going to show with Giselle and Pocho is our new ideas that are getting together to think new VMs and with new ideas and pushing a pushing group that is trying to create a new VMs and with new technology and people here in Argentina. So thank you for coming, and you have 30 minutes.
Hello, my name is Boris Shingarov. I work at Labware. I do Smalltalk VMs. I've been doing Smalltalk VMs for 25 years, and nothing else but Smalltalk VMs. I have presented a number of times here at the Smalltalks conference with ideas of bringing the Smalltalk VM way to the future. And a number of things that I had already presented, they're related with having a Smalltalk with no VM at all, where it is Smalltalk all the way down to the microprocessor, or potentially even right to the gate level. You can write a Smalltalk processor in Smalltalk so that it is indistinguishable from the image. But today I'm going to talk about something that we discovered last year, which is quite shocking and unexpected. One of the new requirements for bringing Smalltalk to the 21st century stems from the idea that we cannot do software that appears to work. My first job writing software was for a firmware for a surgical instrument for heart surgery to do on patients with Fallot tetralogy. And in that kind of software, you cannot just go, okay, it crashed, we're going to fix the bug because the patient dies. And the group that was tasked to work on that was back in the Soviet Union, was the actual former group that was working on nuclear safety. So in that mentality also, you cannot, oh, okay, we just killed 5 billion people, okay, we're going to fix the bug in next release. It just doesn't work. And the idea is that today, if we are looking for expanding new markets, they require that kind of reliability. The demand for that is more and more every day. And if we're looking for expanding Smalltalk into those emerging markets, we cannot simply write programs, because the way how you write a program is you write it, you kind of do some hand waving why you think it is going to work, and then you do testing. Testing means you throw a bunch of particular test vectors or parameters that parameterize the test, and then you see what it does, and then if the behavior resembles something what you think is correct, then you say, oh, okay, it appears to work, I'm done. Well, what if in production it is with something that is not one of those test vectors that you gave it, so you don't know how it will behave. I was trying to do in this VM that I've been writing, all in Smalltalk, I looked in the last year, I started looking at, okay, can I verify parts of some traditional VM, like COG that we have for open, Faro and Quiz and whatever, Smalltalk. And I said, okay, can I prove it correct? And the answer is no, simply because it is not correct. And the trouble that I found is that you model the VM when you write it in, well, okay, it's a pseudo Smalltalk, you write COG, is that when you write it and when you debug it in the COG simulator, you are looking at a model of the microprocessor, and it has, for example, some registers and some memory, and things you put in it in the debugger and you're looking at. There's small integers and large integers, and these members of the Z set of integers. As Smalltalkers, we are very, very proud that we have modeled this very nicely, so it's all transparent and so on. But when you look at what the actual processor is doing, the computational entities that it operates on is not integers at all. They are ints. They are machine words. So, for example, if you have 16R FFFF and you do +1, yeah, it's a small integer, but it's a small integer modulo what machine word length, and depending on that, the processor is either going to overflow, and that is set a carry flag or an overflow flag, or it's just going to become 1, 0, 0, 0, 0, right? We don't have a model of that in Smalltalk, and that is what we need to be able to formally reason about what's going on, what the VM does when the actual microprocessor executes those instructions with those entities, because those entities are not integers, they're ints. So the very first thing that I added this year compared to previous years, I added to the Smalltalk class library a hierarchy of machine arithmetic. So let me show you what I mean. So the basic creation for an int value as opposed to an integer value is, let's say, it's the value of 42, but put into a 32-bit long integer. And then we have this x, and I will show you if I debug this, my x is now I have an x, and it is a bit vector of length 32, and the value is 2a in hexadecimal. So, okay, the next thing I need to prove the correctness of, well, in this case, the Smalltalk VM that I'm writing in Smalltalk, is the ability to not throw just simply particular parameterizations of the test, but unknown variables. So if I have, let's say, an Intel processor and I want to put into register ECX, I want to put x squared minus 2y. So how do I put something like that into a register of a microprocessor, right? So for that, I need a system of computer algebra that I need to have in Smalltalk. And I start with the simplest thing, which is int symbol. And an int symbol is the same thing. I simply say that it is, again, a bit vector of length 32, but the value of that is x. And I can multiply that by 2 and subtract from it y, a similar bit vector, with the symbol y, and that's going to give me an AST tree. An AST tree is again going to be just a bit vector of length 32, but it's just an abstract AST, who knows what's there. And when you throw this into the simulator of the processor, which is exactly the same simulator that I was deriving from the processor description language in the previous year, is just now is augmented with this ability to not only work on actual values, but on these computer algebra expressions. Right. So let's see how far I can go with this. Well, a simple test that I will show you is this one. There's a concrete increment EAX. So it's a very simple instruction. On the Intel processor, it is just this 1 byte hex for 0. And I say that my architecture is IA32, but I can move 5. So let me execute one instruction of this processor, which is a model that is synthesized from the formal description. It's all smalltalk objects that are given by this parser of the formal specification. And I get a final state. And let me look at this. Now I started from Girex 100. Now the instruction pointer advanced 1 byte, so this is this here. And let me look at EAX. EAX is actually 6. Well, this is uninteresting, right? Because I want to be able to prove things, not just test things. So if I give it a symbolic thing, I put X into register EAX and execute one instruction, what's going to happen? You can guess, right? So what's happening here is instead of 5, I'm putting X into it, which is this, right? I put it there, and now my simulation state, if I look at the registers, it's exactly the same thing, but EAX is now X. And the bit slices of it, which is, the high, low, is 16-bit, they're just bit slices of that X. So it's an algebraic expression. These are actually ASTs. And then I increment, I process it, and then here's the final state. Where's my final state in here? Final state, again, I am at instruction pointer at 101, but this is now, why can't I, that's a bug. But this is a bit vector of 32 bits, which is 1 plus X. And then I do something really interesting. I assert that that value at regs, in the register EAX, equals X plus 1. So this is the critical idea. How do I prove? So basically, the equals message on the AST is overridden in a way that I am asking a SAT solver, which right now we don't have in Smalltalk, but I will show you in the lightning talks, the beginning of how our round Smalltalk solver runs on this one. I'm asking the SAT solver, can you go through all different possibilities for X and find a counterexample, such as EAX does not equal X plus 1. And if it can find a model for what I'm asking for, then I found a bug. If it returns unsat, that means that the original theorem is in fact correct. And SAT solver, it will give you a proof tree that it is unsat. And that proof tree that it gives you is the proof tree that actually shows you that there are no possibility, that there is no possible input where the result is not what we want. So this is just for an instruction. So how can we apply this to the Smalltalk VM? So the idea is something more than what I showed you, because this has been going on in different branches of computer practice for quite some while now. The security people, they're using this very widely. There are binary analysis frameworks that you can throw at them any binary executable on many different processors. And what they will do, they will, for example, synthesize input that will cause a buffer overflow and cause execution of arbitrary machine code that you want. And these have been very, very successful, and there's a big following. Where we do something that nobody else does is when we model self-modifying code, because when they hit self-modifying code, so let's say you have a pick that is patched, or for example, your JIT just generated some binary, and after executing the JIT, you do a jump, and that jump jumps into the generated code. All of the existing tools, at least that I know of, they go into an exponential combinatory explosion. And this is because they execute binary code, which is known concretely, with a symbolic algebraic input. But if the instructions themselves are symbolic, the tool cannot deal with it. So what we did in the last 6 months is a system which is more advanced than the existing state of the art in symbolic execution. This is the only existing system that can execute actual algebraic code itself. And the reason we need this is what we do is we run the actual JIT symbolically, and before we jump into the beginning of the end zone, the state of memory, like the instruction memory, is itself, it has holes inside the instruction encodings, and it has taken me a few years to understand how to do this, because the original target agnostic VM that I've been showing for roughly 5 years, 6 years now, what it did was it had models of instructions, and then when you have selected instructions, you have to fill in all of the operands, so you know what the values of the operands are. And after that, you can emit the instruction. You do it target agnostically, but the problem is that if you don't know some part of the instruction, it's just going to give you, question marks and saying, well, these bits in the instruction encoding are not known. Well, I'm not going to, due to shortage of time, I'm not going to explain in much detail what this is doing, but I'll just show you how what happens with instruction encodings. So let's say these two algebraic instructions with x and y, which are two parts of the argument to the JIT. I'm trying to do a load 32 into register self in this case. So let's say this models the behavior of the JIT, and now I've got. It's going to take a little while. Now I've got instructions, which is 2 instructions of the power PC processor, so add immediate and shift, and then OR with immediate. And the instruction itself, it has a bunch of bit fields over there, but I also know what the encoding is. I know that my binary encoding is actually this. So it's a 32-bit wide instruction, and there are bits that I already know, and then this is an AST that is parameterized of my original parameters. This is the highest 16 bits. And on the other instruction, I have, again, some instruction encoding here with some bits that are an AST over the algebraic argument that I gave it. Well, the cool thing is that I can actually run it on a model of the processor, which is a bunch of Smalltalk objects, which I instantiated by parsing the formal specification of the processor. Well, this is how it works currently, but there's nothing to stop us from, for example, simply looking at a Verilog of a chip and arrive at exactly a similar model, and this has been done in some experiments together with the RISC-V formal group guys, because they have a front end that is doing it. So now I can instantiate a state and yeah, this is and lift the basic block that contains that instructions, because unless you group them in basic blocks, as Giselle explained yesterday, you get extremely poor performance. And then we just do exactly the same processing and get in the final state, it converged. So I went from 1 to 108, and now in register 3, I have X. So what the algebraic engine, or the system of computer algebra, what it did, it diverged. So in different registers, or in the different flip-flops somewhere in the processor, it contained very complex expressions, or ASTs that are having X as the parameter. But at the end, we say simplify, and it simplifies that big polynomial using Grobner basis. It just simplifies it to some kind of algebraic normal form, and this normal form is again what we gave it. So I can ask the SAT solver here to assert whether R3 equals X. And if that assertion comes to be always true, that means the whole JIT, which can be, I don't write it, it could be a traditional JIT written in C or C++. I just compile it to native code, I execute that native binary, and then I run it here, and then I jump to the code that it executed, and I execute that. And I look at the state of the machine at the end of all of these possibly billions of instructions. And the cool thing about the state of computer science today is that the SAT solvers have gone so sophisticated these days that it does not suffer from combinatorial explosion. That it just linearly propagates the constraint all the way down. So this is how I can prove that a particular JIT correctly performs translation on any particular sequence of byte codes. But it gets better, because I can ask the SAT solver what instructions does the JIT needs to execute in order to come up with a sequence of native instructions in the instruction cache, so that if I jump to it and execute it, the result will be all that. So what I can do is stop writing JITs at all. Writing the JIT is basically writing a bunch of test cases, and I say a correct JIT is one that passes all these tests. And I am asking the SAT solver to backpropagate these constraints and give me a sequence of instructions that will function as a correct JIT. Now, I've tried about JITs and to see that it works, but in the future, I don't see why this cannot also be done for things like synthesizing your polymorphic inline cache, for example. And in this way, you have a VM that is totally unspecific to any processor architecture. You will see later in the day with Poch's presentations and Jan's presentation, and later possibly a lightning talk that I intend to do about actually showing these things I've brought a Sci5 Unleashed board. This is the latest engineering sample from Sci5 doing actual RISC-V hardware. So we will, as the day progresses, we will do 2 or 3 or 4 demonstrations how this technology actually runs actual code on a processor of the future, we hope. And with this, I will pass the mic to Giselle to do the next.
Okay, but questions first. Thank you first. Yeah.
Hi, Boris. Congratulations for a great talk.
Thank you.
I have a quick question about the machine arithmetic you showed.
Yes.
You showed a test where you instantiated x and then you incremented 1 and
Yes.
finally asserted that the final value in the register was x plus 1.
Yes.
And you said that the SAT solver couldn't come up with a counterproof, so you know that holds for every value of x, right?
Yes.
But what if the value of x is like f? So it wouldn't be true, right? That it's x
yes,
plus
it
1.
is, because it is actually true, right? Because if you do int value, actually no, 16 are FFFF as bit vector of length 16, and these are signed things, and if you add 1 to it, the actual result you're giving, because remember, these are not integers, these are Gaussian moduli, and when you add 1 to that Gaussian modulus, length 16, you actually do get 0. So that's the whole idea of this machine arithmetic, is that it is a faithful representation of how the microprocessor does addition and multiplication and all of these operations. So if we actually inspect here, you will see that it is 0.
Yes.
So that is the source of bugs that you cannot debug in the Cog VM, because in the debugger you will get 1, 0, 0, 0, 0, and on the actual microprocessor when you run it, after it is slang translated into C and then you GCC it into machine code, the microprocessor does something that you have in the simulator when you debug the VM, you have absolutely no idea what's going on. And these bugs, I have been following this whole work. I started it about a year ago to actually see what's going on with the COG thing, because I wanted not to just run toy small talks like mod talk, but I wanted to run quiz on my VM. And the problem with the current machine is that if a bug like that happens, and I have seen on the mailing list, there are a bunch of bugs that, well, the production VM, when I actually compile it, it crashes in mysterious ways that when I do the same thing in the development environment, the bug doesn't happen. It is perfect. And by looking at what the majority of these bugs are, I found that it is a discrepancy, and I also discussed this a number of times with Clement Berat, and he said that, well, this is the work from a technical perspective, this is the worst pain, because the production VM and the debug VM, they diverge, they behave differently, and this is the solution to that, because we don't do this kind of problem, because we have in the Smalltalk class library, we now have a model of these computational entities that the microprocessor is actually dealing with. So that class of bugs is just completely eliminated.
Okay, thank you, Boris.